Hello everyone, I am Bhimama Bhavikati. I am studying in BSc second sem PCM combination in Sri Siddheshwara Government First Grade College and PG Studies Center Nargund. Today I will explain band theory of metals to explain conductors, insulator, extrinsic and intrinsic semiconductors including temperature effect. The contents is introduction of band theory. Band theory. Example of band theory: conductors, insulators, semiconductors, intrinsic semiconductors, eccentric semiconductors, extrinsic semiconductors types. The introduction is: band theory is similar to the molecular orbital theory of covalent bonding. According to molecular orbital theory, when two atomic orbitals of nearly and same energy and same symmetry but belonging to two different atoms combine or overlap, they form two molecular orbitals. One molecule with lower energy called bonding molecular orbital and another molecule with higher energy called antibonding molecular of orbitals. The band theory. As a result, a large number of energy levels are crowded together into bands. Because of the energy bands, the molecular orbitals theory of bonding in metals is also known as band theory. The atomic orbitals of three or more atoms overlap to form molecular orbitals that encompass all the atoms. Molecular orbitals are said to be decollized. In metals, the outer orbitals of an enantiomers numbers of metals atoms overlap to form an enantiomers numbers of molecular orbitals that are decollized over the metals. The example of band theory: the formation of energy bands in a lithium crystals. When any number of lithium atoms combine to form a lithium crystals, there will be a formation of three types of bands: 1s, 2s, and 2p. The electric energy band where electrons can move are called conduction bands. Two conduction bands are separate from each other by energy gap called forbidden zone or gap. A solid crystal is supposed to contain energy bands. The energy bands formed by the inner energy levels are very narrow, while those are obtained from the valency levels are quite wide and called valency bonds. This is lithium crystal lattice figure. The valency bonds formed by the inner energy levels are very narrow, while those obtained from the valency levels are quite wide and are called valency bands. The valency bands which are completely filled are called non-conducting bands. Those which are partially filled are called conduction bands. The energy gap between the two bands is high. Then the promotion of electrons from the lower non-conducting bands to the higher conducting bands is prevented. The conductors. Metals are conductors. Metals are good conductors. Metals contain plenty of electrons and available for conduction. The conduction band of a conductor is partially filled and contains a very large number of electrons. Electrons can be promoted to the nearby vacant energy levels in same band by electric or thermal energy. Band explains the same band by electrical conductivity of metals. Increasing in temperature sometimes leads to decrease in conductivity of the metals. Insulators. Insulators are bad conductors. The large energy gap between the lowest vacant energy and the highest fully filled energy band. The electrons cannot be easily promoted from fully filled energy band to the vacant energy band. The energy required for shifting electrons from the completely filled valency to the empty conduction band is very high. This is insulator's figures. This is conductor's image. Semiconductors. Semiconductors are materials whose electrical conductivity lies between those of conductors and insulators. In a semiconductor is lesser energy gas between the two energy bands. The electrons are not very easily excited from the filled to the vacant energies bands. At this can be excited if an appropriate amount of energy is made available. Semiconductors is two types: intrinsic semiconductors and extrinsic semiconductors. This is semiconductors images: silicon, germanium, etc. In, in, Intrinsic semiconductors. Semiconductors in their extremely pure form are called intrinsic semiconductors. Examples: silicon and germanium. Intrinsic conductors are at room temperature and the conductance of silicon and germanium is extremely low. The four valency electrons are covalently bonded with neighboring atoms. There are no free electrons for conduction at higher temperature. Some of the covalent bonds get broken. Electrons are filled. These electrons cross the small forbidden zone present between two energy bands. Thus, after crossing the electrons, they leave positive holes. To these positive holes, electrons of adjacent bands migrate. This causes the positive hole to move in a direction opposite to that of electrons. Intrinsic semiconductivity increases the temperature because more covalent bonds are broken and more number of free electrons are formed. This is example for intrinsic semiconductors: silicon bond gap and intrinsic semiconductors of silicon. This is intrinsic semiconductor of germanium. This is bond gap of germanium, and this is germanium crystal at OK. Extrinsic semiconductors. Extrinsic semiconductors are at room temperature. Silicon and gallium can be made semiconductors by adding certain impurities. The addition of controlled amounts of impurities to semiconducting materials is called doping. The added impurity is called dopant. The extrinsic semiconductors are two types: an N-type extrinsic semiconductors and P-type extrinsic semiconductors. The extrinsic semiconductors types 1 is N-type of extrinsic semiconductor. The negatively charged electrons are responsible for conduction. They are called N-type semiconductors. When atoms with 5 valence electrons like arsenic, phosphorus, antimony group 15 elements are added to pure silicon crystal. Each of the dopant atoms replace one silicon atom in the crystal. It completes bonds using 4 of its electrons with silicon around it. The 15th electron remains free. These free electrons can now conduct electricity at higher temperature. The filled impurity levels of has phosphorus are located quite close to conduction bands of silicon and gallium. P-type of extrinsic semiconductors. In order to fill these hole an electron from a neighboring responsible for conduction. These are called p-type extrinsic semiconductors. When atoms with 3 valence electron like boron, aluminum, group 13 elements are added to pure silicon crystal. Each of the dopant atom replaces one silicon atom in the crystal. It completes only 3 bonds with silicon around. At the place of the fourth electron, a hole is created. The conclusion is band theory provides a fundamental framework for classifying materials based on their valence and conductions and gap. Conductors features overlapping bands for free electrons movement. Insulators have large impossible gaps. Semiconductor possess a small thermally manageable gap. The ability to manipulate this gap, for, particularly through temperature and doping, is the foundation of modern electrons. Conductors are inversely proportional to the temperature. This means conductors increases, the temperature is decreases. The temperature increases, the conduction is decreases. Insulators are even with rising temperature, the energy provided is usually insufficient to overcome the loss. The semiconductors are as temperature increases, more valence electrons gain to jump across the band gap, reducing resistance and increasing conductivity. Thank you all.